in reality is made up of a bunch of transistors, about 20 transistors that go into that. But we will treat it as a block. We will look at an op-amp as a block and look at the operational details and calculate its behavior. There are three terminals to an op-amp. Number one is it shows negative here. So negative tells us this is, and this is what we call inverting input. So the signal that comes in here would show up 180-degree out of phase. The second, and that's number one. Second terminal is what we call non-inverting, right? So the signal, whatever comes up, shows up in the same phase. And of course, like we discussed before, when it's amplifying this extra power or the power that's dissipated during the operation, those are supplied by external power supplies. So an op-amp would have 5 terminals to it, right? But we are only concerned with 3 of those. We take the power supplies to be granted. But power supplies are there and they can have an impact in real world applications, but this is how you would write your power supplies. Now, an op-amp has few characteristics which we have to know. We have to remember those because whenever we are dealing with op-amp, we have to just remember that it has infinite input impedance. All right, number one. It has 0 output impedance. Number 2. Number 3, it has infinite gain, which means infinite, right? The ideal behavior. That's number 3. We keep on going and there are 2 more things. Common mode signal. So when you say terminal 1 and terminal 2, if same signal is fed in both of those, it would reject. It does not amplify common mode signal. It does not amplify signal that appears same signal if it appears on both terminals. So which means that only the difference of 2 signal is amplified. All right. So now, if I have to write that down, I would say, okay, at the output, at V out, what I get is going to be the gain multiplied difference of 2 input signals. This is the very basic fundamental relation that what we get at the output is the gain, and that's coming from the op-amp. All right, so which just tells us that it's the difference that's important. Difference is what is amplified. Now, when you say the input impedance is infinite, that means the current cannot flow into op-amp. There's no current flows into the op-amp. Now, and on the other end, the output V0 or VO would be between terminal 3 and ground. So it's 0 impedance. Anything can flow very easily out of it. The output at 3 is in phase with the plus sign. Terminal 2, it's out of phase with terminal 1. All right, what else about, yeah, so bandwidth. Op-amp can amplify DC 0 hertz all the way to infinity hertz. So it has infinite bandwidth. It can amplify anything that's fed to it. These are the ideal conditions. These are the properties of an ideal op-amp. Now, this is something which is showing what you can call open loop, right? There's the inputs are independent of each other, and the output is something which is the gain times the difference of those. But that's not how we use. That's not what is beneficial for us. We use it in ways where we use some feedback resistances. And this is the configuration, what we call inverting configuration, because the input signal is fed or input through terminal 1 through the inverting input. Now, here we can see the signal there would be a difference of signal between these two, right? So we would call it a differential configuration. But if, now I go back, but if we are applying the same signal on both terminals, that would be what we'll call a common signal or common mode application. That's something which would be there, which can be there. But how do we calculate how much is the signal, or what is the difference between the differential signal and the common mode signal? So let's take a look at that. We input differential, VID, is the difference between those two signals, right? And this is what is coming here to the terminal 1 and terminal 2. But if it has a common mode signal to it as well, so we have to see how much does get to the terminals of the op-amp. If I write the common mode signal as we input CM, that would be then average of two input signals, V1 and V2. This is CM. So that would be half times V1 plus V2. And we can use these two to find the voltage at terminal 1 and voltage at terminal 2. So that would be then V1 would be the common mode minus the differential, the average of differential signal, the half of differential signal that gets there. And V2 would be the sum of common mode signal and the half of differential signal that gets there. But we will, when we analyze, we will start with the differential and common mode, and then we'll build up on top of that. So the ultimate idea is that there may be both signals in the input, and then op-amp will manage or deal with different components of those when it's doing the amplification. And in that case, then both would have their own amplifications, their own gains, which will then show up as the gain of the differential signal across the output. We will not go too much into the internal operation of the amplifier, but we'll see how do we use it in circuit, and what we are generally interested in gain. What would be the gain and how we can control it. Now, coming with that, the 5 things which I said, there's one of those was it has infinite gain, which means that if I were to write my output signal, which is gain times difference of the input signals. This guy is infinite, but this guy is finite. The output is always finite, right? So output is something that you can measure. Output is something that we want to use to do something useful. How does that work? So let's do some analysis on this, and that will help us make sense that what is the benefit of this and how does it help. Now, in this situation, this is the resistance at terminal 1, resistance between the non-inverting input and output, and this is basically feedback resistance. And this is an example of a closed loop configuration. First closed loop configuration, but then we'll see non-inverting configuration. In the inverting configuration, the op-amp in device is used as a passive component. So we can adjust some things to adjust that. We would like to adjust some things, and so we can adjust the gain. For an ideal op-amp, the gain is infinite. How do we work around? How do we deal with that? Now, there are few steps, and please follow with me when I go through, because that's something which will come over and over. We have to see that when A is very large and this is finite, this has to be small. So V2 minus V1 has to be small, which means the smallest is they can be, the difference can be 0 and they can be equal, right? So we can have some finite output for those. If I say this, that directly means that these 2 points are following each other. These 2 points are trying to get to the same value like each other. And we call this virtual short circuit. So when we look at the ideal behavior that translates into this idea that number 1 and number 2 are shorted. Okay, if they're shorted, what does that mean for our circuit? So there is a bunch of things that would happen. Let me get to the next slide. And that's what we have shown here as starting from number 1, number 2, number 3. So let's follow these numbers. The first thing is that there is zero potential, zero voltage between number 1 and number 2, right? So they are at the same potential. The second thing that happens with that is that number 2 is now at virtual ground, which means the voltage at number 2 is 0. If that's 0, how do we calculate the current that's coming in is going to be between this point and this point. It would be V1 minus, sorry, VI minus V1 divided by R1. That should be the current I1. But this guy, we say this is at virtual ground. So this is 0. So what we are left is this is the I1 current. Now, an op-amp has infinite input resistance, which means the current cannot go to op-amp. The whole current is now going to go to R2. So number 4 is no current can go inside, which means the current through R2 is the same as the current I1 that was flowing in from the signal. And I2 is then equal to the same current that's flowing here. So it's get a little bit dirty, but if you have followed me, let me just clean this up a little bit. All right, so, but then what is the output voltage? From this guy to this guy, there's this resistance. So, but there's current flowing because of the difference of these two voltages. So if I were to write that down, this is I1. So I'm writing 0 minus I1 R2, the potential on one side and the potential on the other side. This translates to this guy. So if you simplify this, we get to this relationship. But we remember gain from first chapter, gain is equal to V out over V in. If I rearrange this, what I get is my gain V out over Vi is equal to minus R2 over R1. So my closed loop gain is finite. We started with infinite open loop gain, but non-inverting configuration has done something interesting. It has taken that uncertainty out of that circuit where gain was infinite. But now we can control the gain by picking right values for R1 and R2. Does it make sense? Are you with me on this? Now, which means that the value of my resistances are going to define the gain of my op-amp circuit, right? So that's the first and most important implication of doing this analysis in steps. Now, let me take a look what's. All right, so which means my closed loop gain is this. So there's example that if R2 or the ratio between R2 and R1 is what we decide. If you pick it to be 10 and you have 1 volt sine wave input, what is the output? Can somebody calculate it right away? Can somebody calculate it right away? So this is simply very, very simple formula. What you have is the ratio of these two, plug in the ratio of these two. You know this guy, what is this guy? All right, who's giving me the answer?
It's 10.
10? 10 what?
Volts.
10 volts, all right, very good. What else? So look at the input, is it just a DC?
Input is 1 volt, sine wave.
Sine wave, all
Peak,
right. So
peak to peak sine wave.
P to P, so we have to write PP like the way it's written in the input. 10 volt peak to peak, all right. What else can you say about the output? Did you calculate it? Lester, did you calculate it?
Which part? The
Or you just
two
eyeball it?
resistor one? Yeah, I just eyeballed it.
All right, so that's where you have missed the minus sign.
It's negative.
Oh, I see.
And when you say negative, what does it mean for the signal?
It's inverting.
It's inverted. It's 180 degree out of phase, right? So please don't eyeball electronics. When I say do it, do it. So because there are components to that have to translate into what does it mean. So what we have done is we have now taken the gain in our control, and we can precisely define the gain. Another interesting thing is the value of R1 and R2 are not important, but their ratio is important. So you can just have cheap, very low value resistance and be able to acquire the gain. So you don't have to, so you get the idea, it's just the ratio that's important. So we have got the control, but what have we lost? What have we lost? We have got the gain, but we have lost some accuracy, right? Because the resistance, it has their own kind of tolerances, but we're still good enough. We'll still be getting a circuit which can give us a finite gain. All right. Now let's take a look at finite open loop gain. This was closed loop gain. So what is the effect of finite open loop gain on our circuit? Again, so this is how we find the resistance, input and output resistance. Before that, I want to touch on the gain, finite open loop gain. So we got the open loop gain as output voltage over input voltage. Again, many times VI and V1 would be written like this. So make sure these are two different things, right? VI is what you find here. V1 is what you find here. VI is what is coming from the signal. So please, if I mess up, please let me know. And be careful when you're doing this to make sure we are using the right voltage in calculation or your analysis.
The V1 is the node part?
V1 is at terminal 1, right? Okay. But VI is the input. VI may be applied on terminal 2. But when we are dealing with 1, so we have to, so please keep an eye on it. I may mix them. I try to write small I. All right, so from this, I can get my input voltage to be, sorry. No, where did it go? Jumped ahead only. All right, so just playing with it. So but this is applied on number 2. So we need to have a negative sign with it. So then the input would be minus V naught over A, V output over A. Now this voltage is going through R1. And the current through R1 would be then the difference of the two voltages divided by the resistance itself. And that would simplify to be input voltage plus output voltage divided by gain divided by R1. So the op amp has an infinite input impedance. So the I1 is going through R2. So what is the output voltage then? So from this point to this point, we have to find that the difference, which would be minus V naught A, which is, we are taking it from here, minus the voltage drop across R2. Are you with me so far? Now I can plug in I1 value here from this guy. And this gets to something which is minus output voltage over current over, gain minus VI plus V output over A, whole thing divided by R1 times R2. Just a bit messy, but the thing that we are going to see here is that we have the input voltage and the output voltage, and we started with open loop gain, but now we want the closed loop gain from that, which is V naught over VI. And that simplifies to be something with R2 over R1, whole thing divided by, I'm just gonna write here, 1 plus R2 over, there's another 1 plus R2 over R1 times divided by A. That's in the denominator. Now, if this goes to infinity, this factor goes to 0, and what we are left is this guy. Again, the gain is getting to ideal value. So even if we start with open loop gain, we end up with the same relationship where gain is dependent on the ratio of R2 and R1. Just coming through the open loop gain with finite output. So we had to, what we see is again, we reach the same number. But this puts a condition now that A has to be large than this guy. So now on the ratio of R2 and R1, like we were seeing, there's one more condition to that, that 1 plus R2 over R1 has to be much smaller than the open loop gain. So these two conditions have to be satisfied to get the closed loop gain, to control the closed loop gain, and to minimize the dependence of the gain on the open loop gain of the op amp. Are you with me so far? I'm sorry, it's a little bit crummy, but there's maybe I'll add more open pages going forward to have easy write up there. All right. So how do we find input and output resistance? For the ideal op amp, gain is infinite. So we take the input resistance R1, and this, the input resistance of the signal, I haven't written here, so R input, this makes a voltage divider with the signal. So we want the ratio to be high. So R2 is much higher than R1. So the voltage, major voltage division then should happen here. But then this puts restriction that we need to have very high feedback resistance. And that's not something we like to do. So there's a way around. Instead of using this, we use an equivalent circuit to use smaller resistance, but still achieve the high overall resistance in the feedback loop. All right, so let's get to an application, what we call weighted summer. So yeah, this is the idea that instead of having a very high feedback resistance, we can use parallel resistance in the feedback, and this increases the current flowing through the feedback resistance network, and the voltage drop is higher around this. So voltage divider is giving you more power on this side than being wasted here or here. So in your lab, if you are creating a feedback loop and you are using only, and you are given only small resistances, to achieve high ratio between R2 and R1, this would be a way around where you would put the parallel resistance network in the feedback loop. All right, so just some practical things on when you are actually making a circuit. So going from ideal to actual circuit. All right, so let me clean this. All right, questions? So first application, weighted summer. So what it's doing is it's taking a bunch of signals and amplifying it based on the weighted contribution of those currents. When you say weighted, what is mean is their relative difference. It's the output is a weighted sum of the input signals V1, V2, V3 that are being fed to the circuit. We're just looking at the top left circuit right now. What we are doing here is there's one feedback resistance in the negative feedback, and that has to play a role with each one of these resistances now. So this and this, this and this. So what we end up doing is then finding all those number of input signals and adding the current contribution from all of those, but those have to be weighted. All these currents get added up. I is equal to I1 plus I2. That's basic Kirchhoff law up to IN. And the voltages, now this is acting as a voltage divider for each input. And hence, each input is contributing its own weight to the final output that we get. All right, so these are then all the currents are being summed up, and the feedback loop is getting the weighted sum of the input signals. But the inputs are all opposite in signal, so they all are coming to the negative, not the inverting terminal. So we have the negative on upfront. All right, so this is an application where each summing coefficient can be independently adjusted than the others by just adjusting the feed-in resistor for each input, right? So here that the idea of the virtual ground helps us, and each one would have its own voltage divider with the feedback resistance. All right, so we can sum positive and negative both types. So for example, if we have the signs are different, if they are out of phase, so we may have to sum signals with opposite signs. So we do that by using two op amps. So one is getting signal in one phase, the other is getting signal in other phase. And once they add up, so in this case, then they would have different signal for these guys because of they are added up here, then they are being, these three resistance are coming up as the parallel resistances for that. And so we get the negative signs for that. So these get inverted, then these get inverted. So their inversion at different levels will result in, if you take these positive, then these would be negative. If you take these negative, then these would be positive, right? So we can take care of the opposite signs of those things by adding as many two op amps. So one would be for the positive and the one would be for the negatives. All right, so we looked at the inverting configuration. Now let's take a look at the non-inverting configuration. So here what we have done is the input voltage is applied to the positive input terminal, and the one end of the R1 is now grounded. The analysis goes in the same way like we did for the inverting configuration. We start with number one, which again for infinite gain, the difference, for the infinite gain and finite output, the difference of V2 minus V1 has to be small again, which means it has to be zero, which means again, these two are on virtual ground. They are virtually shorted. They're virtually short-circuited, so we can have a finite output, and that results into the differential voltage to be zero. So if there was differential voltage, that would be zero, and V plus would be now equal to V minus. And that's the input voltage, right? Which is now being applied to non-inverting input. Now, what happens to the current? The current through R1 is thus due to the input voltage and the ground. So these are shorted, which means this voltage is the same as this voltage. So the current from here to here is now because of V input. Still with me on this? So number one was the difference is zero, which means they are virtually shorted. They have the same voltage. Now, then we have to look at the current that's flowing through R1 that can be taken as due to the same voltage that's applied on the non-inverting input. So hence, the current I1 is this guy, which is V1 over R1. Now, where is this current coming from? The op-amp has infinite input impedance. So there's the same current then that's coming through R2, right? So if that's the case, then my output voltage is combination of this voltage that's at this point plus the voltage divider across. So this guy is I1. So voltage drop across R2, right? So this is I1 R2. So this is the voltage drop across this guy. So my output voltage is then sum of these two voltages. And I can take VI out, and what it leaves behind is 1 plus R2 or R1. So what would be the gain? Can somebody tell me the gain for non-inverting configuration closed loop? So what's the gain here? Let me clean this up. What's the relationship for gain?
Is it RF over RN plus 1? Or
1 plus?
RF over RN? Or,
No, we don't have RF here.
oh,
Okay, tell me what
2 over R1?
what should be, okay, what's a simple equation for gain?
V out over Vn.
V out over V in, right? So, and we see that now here. So what should be the gain of this circuit now? 1 plus R2 over R1. Again, the most important thing has happened is I've taken the infinite gain from the op-amp, and now we are controlling the gain by adjusting the resistances that we use, right? So Rn, R1 and R2, which are acting as voltage divider to feed the output voltage. It's feeding it back to the inverted input terminals, and it is giving us control over the gain of the circuit. Now, if Vi increases here, if I go back, so that's one thing. So the gain for non-inverting is, we've got this. What is this? Sorry, this is jumped ahead of me. All right. So we'll see the next slide, but just wanted to sum up a couple of things that this is the gain. But now there are some other issues here, some other parts of the analysis that we have to take a look at. If Vi goes up, if me just clean it up a little bit. So now if this goes up, the differential signal goes up. VID will go up. And that means our output will go up, right? Which is the basic behavior of op-amp. But the fraction of this increase goes back to the, through this, to the inverting input through R1 and R2. And this will then counteract this guy, the differential voltage. This will then, the feedback will bring it down to 0. So what it means is that although op-amp is supposed to be amplifying the differential signal, but in case of non-inverting configuration, op-amp result does something what you call degenerative action or degenerative feedback, where it would bring down the differential signal if it is changing from the basic value that's running the op-amp. And that gives us control over the gain of the network. All right, so now in the non-inverting configuration, there are a couple of things that we have to see, that it's a finite loop. So using the resistances adds up the error into the overall gain, right? Because of their tolerances. So what we have to do is we have to then have a restriction that A has to be, that what we talked before, A has to be much, much greater than 1 plus R2 over R1. So we have less dependence on the variations of resistances. And what we are left is what we saw before, 1 plus R2 or R1. And there's still error. So that's measured by multiplying it with 100, and that gives you the gain error because of the differences between the resistance tolerances. All right, so another application is for op-amps is what we call voltage followers. Because of their high input impedance and low output impedance, we can use them to just buffer between two circuits or two components. And in that case, it would just follow the input voltage and give the output voltage according to that. That's one application where we use that. And the circuit is very simple. It's, let me see if I have it here. That circuit just uses just the feedback without any resistance. So you have the input signal on non-inverting terminal, and you get what you call a voltage follower. So just simply output follows the input. And this is unity gain amplifier, which is just used as a buffer between two different needs of two circuits or two components. All right, now there's a couple more applications which we can take a look at, and then we can call it a day. One is difference amplifier. If you have long cables running, for example, musical instruments, and if during the transmission of signal between two cables, if there is any difference of those signals, the difference amplifier can get rid of those. So if you see those differences, it can get rid of those. So it responds to the difference between two signals and rejects the common signals. So going back to this discussion that we had before, it can look at the signal and get rid of these the common mode signal, and it would amplify only the differential signal. So practically it's if this is nothing but the gain, differential gain times the differential signal plus common mode gain times the common mode input. So again jumped. So common mode, so it's nothing but this, and you add up and we get a simplified relationship for the difference amplifier like it's shown here. And for the effectiveness of common mode rejection, we have something called common mode rejection ratio, which is measured in dB, and all it does is it tells us what is the effectiveness of the amplifier in rejecting common mode and amplifying the differential signal. So CMRR is a parameter that we know and we use for our circuits to see that how effective it is in rejecting the common mode signal. And we use them as transducers that have small output, like 1 millivolt. And this, we use them, for example, these two wires that run from transducer to an instrument, which may get interference. Some places we need differential amplifier. So in all cases, op amp with infinite gain that makes it, in these uses, we can control the gain, and what we achieve is we reject the common mode signal. All right, so questions. Another application is instrumentation amplifier, where again, what we are doing is we are using differential amplifier with low input resistance. This guy is the voltage follower between two input terminals, and what we get is we get voltage gain, and we get to reject the common mode signal from these. So first stage does the bulk of gain. The second stage is differencing between the signals and rejecting the common mode signals. So this is what we call cascade amplification. A1 and A2 are just voltage followers, and A3 is being used as a difference amplifier. On the difference amplifier, we can calculate the output that's coming here. So both of those have to be equal, and the gain that we get from them for differential signal is, I'm just going to write the simplified, it's supposed to be V output divided by the differential signal, and that's a factor of R4 over R3 times one plus R2 over R1. So in this case, our choice of these resistances and these resistances. Of course, they're the same resistances in other places. That's what will give us a control over the differential gain for an instrumentation amplifier. So if the gain of first amplifier and the second A1 and A2, if we want to match them, we have to match their resistances. And the two signal paths would then become identical. So this is what we would use to amplify the differential signal. So we can reject the common mode signal that may come into system because of their capacitances of the cables that are running, or any interference that comes into that. So that's the advantage. The disadvantage is in the first channel here, we are amplifying the common mode signal as well. And this can saturate A1 and A2. And even if they don't saturate, A3 has to deal with these much larger common mode signals. So which would then bring the CMRR down. Remember the figure of merit, which is the difference, which is AD over AC here. And the two amplified channels in the first stage, they have to be perfectly matched. So both of these have to be perfectly matched, because if they're not, there will be, there can be signal between two outputs, which can be taken as difference of signals for the third amplifier, and that can become a problem. So these two have to be perfectly matched to each other. Otherwise, their signal would, the difference of their signal would be taken as differential signal by A3, and that would ultimately show up as output, as a valid output at the end of the amplifier. All right, so now to vary the differential gain, two resistors have to be varied simultaneously. So these two guys have to be adjusted simultaneously, so we can get the differential gain to the numbers that we want. So, sorry, not just the two, the R1 and R2 also. So they all have to be perfectly matched. So we don't get we get the right differential signal out of the system that we want.